So today on the bench we're gonna measure some simple diodes. So currently I'm measuring 1M4007 here on the scope. So I'm feeding in a 100 kHz square wave, which we can see here. So the blue trace is the current through a 1 kilo ohm resistor, and the yellow trace is the voltage over the diode. Just to have it simple. So what I'm going to measure here is the reverse recovery time of these diodes. So I'm going to measure a 1M4007 and a UF4007. They are technically the same type of diode, it's just that the UF4007 is supposed to have a superior reverse recovery time to all that I've read. So we can first measure the 1M4007 and see what reverse recovery time it has. So I've set the scope to 100 nanoseconds per division. So we can see that about somewhere over here it's fully recovered, and that's about 400 nanoseconds because it's 2 divisions. And that's kind of acceptable. So then we're going to switch over to the UF4007, if I can do this. So here we have a UF4007, and that instantly looks far worse. I don't really know why this diode is this bad. But as we can see, it has substantially more current going through it, because the other one was kind of not even half a division, and it's 2 volts per division through a 1 kilo ohm resistor. So it's about 1 milliamp per volt in this measurement. So having like half a division here for like 2 divisions is not much current, and this here is gigantic. So for some reason this UF4007 is really inferior, which is against its datasheet. So because so either I'm having superior 1M4007s that are made to a really awesome specification, or really made beyond what they should be made to, or I'm having a counterfeit UF4007 which doesn't even live up to its own specification. Because the UF4007, it should have actually recovered about here somewhere, not over here. So this UF4007 is like probably 10 times worse than its specification should state that it is, which is a bit sad because that's not what I bought. So yeah, I don't really know why these, that was the wrong knob. I don't really know why these UF4007s are this bad, because they shouldn't be. Like a reverse recovery time of about 500 nanoseconds is really horrid, and like this here looks far more horrid than the other one. So like this here looks far better. So that's not really good. And the measurement setup I'm having is actually fairly simple. So, or actually I can leave all wires attached to this. And let's see if I can bring this into camera view. Or maybe I could just bring down the camera to it. So time to go handheld. So where do we have it? Maybe I shouldn't be fully zoomed in. There we have it. So here we have the setup, which consists out of the 2 diodes, which I'm just switching between, and then I have the resistor over here, and then I set my negative point all the way over here. So that's why all the measurement can be kind of fun. But this is how I'm measuring it, and you can measure it in the way you like to measure it. It's up to you. It's just reverse recovery time. I recommend feeding in square wave because that's the easiest to measure with. But yeah, so this is our UF4007, and this is a 1M4007. And this one is supposed to be superior, but it isn't. It's about 10 times worse than what it should be. It's about twice as bad as this is. So that's not really what I had hoped, but apparently that's what you get. And over here it's the signal generator feeding out 100 kilowatts. And okay, I could technically set this to, let's say, a megahertz and do the measurement up at 1 megahertz instead. So let's zoom back into the screen so we can see it a bit better. So here's 1 meg instead. So we can zoom in on that. See what we can infer from this. We're going to go over to our trigger condition, and then we're going to go over to this first one. So this is a 1M4007 measuring at the moment, and it's taking, well, let's take something to point with, and it's going from here to about maybe here somewhere. It's having a bit of positive for some reason there, but this is really noisy because there's barely any current through it, So that's why this up here is really nice and sharp, because we have a lot of current flowing through the circuit and a lot of voltage. And over here the diode is reversed biased, so it's going to restrict current from flowing through the circuit, so there's not as much, so the source resistance increases quite exponentially while it goes down while the current goes down, which is why we go into being really noisy. So yeah, that's why we get noise, because the source resistance increases, because we have a diode increasing the source resistance. But yeah, so over here we can see that we are about recovering, which is about still 200 nanoseconds. So the diode seems to work fine. Okay, it's not working fine if as a rectifier on 1 megahertz, obviously. So we can switch over to the UF4007 and see if it works over here. And no, it still looks really, really piss poor. Like, it's not supposed to be this bad. And okay, I'm driving this with, well, only like 2 milliamps in the positive direction, and well, in the negative direction it goes down to 2 milliamps. Because the signal generator I'm using is not the most powerful thing in the world. So we could try to set it to a higher voltage and see if that helps. But I would suspect that it doesn't. We could actually take a measurement of how many volts we're having over this whole circuit, but I'm not going to do that. That would be complicated. Okay, it wouldn't actually be too complicated. All I need to do is just short the... So let's short the yellow trace to the probe, and then we can see how many volts we're feeding out. So now the yellow trace should be what our signal generator is generating. And we can see at 1 megahertz it's not generating the nicest square wave to begin with, so maybe 1 meg is pushing it. We can go down a little. So let's go down to 100 kilohertz again, which obviously generates a far nicer square wave, but we can measure how many volts this is outputting. So it's about 2.5 down here, about 2.5 down up there, so it's about 5 volts, which is not really what this device is saying that it should output. It states that it outputs 10 volts at current, so that's not really what we're asking for. So we can go into this parameter and increase it a little. Maybe that can give us better results. Let's measure again. See if it's just a current issue. Then we're going to increase this a little. We're going to need to increase channel 2 a little. That's 5 volts per division. Maybe I could just reduce this down a little. There, the counter finally came up. I was wondering where it went. So we set this to exact numbers, doesn't really matter. Let's go back down with this, just so we can try to get as much resolution as possible, because being zoomed out a lot isn't really going to help us. So this is 1 meg for 1M4007, and that's the point we want to measure. And let's measure it. So the point from where it's, so over here somewhere, it's actually going back. So we're going to measure that. Wrong trace. So we're going to line this up with a division, and then we're going to see how long it takes. Then we're going to line up this point with a division, and now we can kind of measure how many divisions it takes. So it's 50 nanoseconds per division, and it takes at least 1, 2, 3, 4, maybe 5, but so between 4 and 5 somewhere, because of noise. So we can't really exactly say where it actually crosses, but we will take 4 just for simplicity's sake. That's still 200 nanoseconds, which is still the same, so no difference there. We zoom out because the UF4007 is way worse. There we have that, and as we can see, it kind of stops leaking all the way over here. So yeah, it's not a good diode. So to what I know, a UF4007 should be superior to what we're seeing here. Like, this diode here is really, really bad. I had actually hoped that these were going to be good, but apparently they aren't. So I'm thinking that maybe this diode is a counterfeit diode. At least it works as a diode. It's just horrid. So Because a 1M4007 is practically the worst diode you can get on the market. Like, that's how it is. It's a general purpose rectifying diode. It's not really that good. So a UF4007 is, at least to the datasheet, it's superior, but this one isn't, which is horrid. So I didn't expect to get that, but yeah. So I need to track down another source for UF4007 and measure again and see if it actually is this bad. Because if a UF4007 is about twice the recovery time of a 1M4007, and the 1M4007 I bought, in other words, this little thing, this here is not, like, I didn't buy this 1M4007 from any reputable reseller, I just bought it off eBay, so it should just be any 1M4007, it shouldn't be all that good. So it's not like I bought it from any like superior source. It's not like it's a Vishay resistor or Vishay diode or something like that, or made by International Rectifier, someone like that. Because then you could probably expect a bit better specifications in it. But if you just buy it from like the cheapest seller on eBay, then you don't suspect to get anything better than a 1M4007. So I'm actually surprised that this 1M4007 is better, about twice as good reverse recovery time as the UF4007. That in its datasheets practically states that it's better than a 1M4007 on reverse recovery time, because both have the same current carrying capability, they have the same voltage or reverse breakdown voltage, both of those are the same, and the only real difference between them is the reverse recovery time, where the UF4007 should be better, but it isn't. So yeah. So now I need to track down a new source, and I hope you all have found this video at least a bit informative, that maybe you shouldn't buy components off of eBay all that often. Or sometimes you can actually buy components off of eBay and actually get what you pay for, and other times you get scammed and get a UF4007, which is really horrid. I actually didn't suspect that. Let's see if I can find something else. Maybe the local electronics store has something better. So yeah, see you next time.